There are three types of strain we need to be thinking about when explaining higher energy present in ring molecules. The first is torsional strain. This is found where substituents have eclipsing interactions with other substituents, and it's in part due to the electrons in the bonds of the substituents being repelled by the electrons in another bond of another substituent. But it is also not so much due to the eclipsing conformation, but due to the beneficial interaction in the staggered conformation, where you have bonding and antibonding orbitals that, when suitably aligned, allow for electrons to provide stabilization to give a lower energy. Okay, the next sort of strain is angular strain, and this is where you have an angle between the bonds that's not ideal. For a tetrahedral carbon, we're talking about not 109.5 degrees, with orbital lobes not optimally positioned, and this will produce angular strain as a result. Lastly, there's steric strain, and this is where a substituent's electrons come too close to another substituent's electrons or another atom's electrons, and they repel each other. Okay, those are the influences to look out for to explain higher energies. But we need to be aware of something else, that most rings are not planar. That's to say, they're not flat. When Bayer devised his strain theory, he assumed they were flat, and that's why the theory didn't fit the practical data. We will start when thinking about rings with the smallest, the three-membered ring, and where all the atoms are carbons. This is cyclopropane. And ironically, given that I've just told you most rings are not flat, this is the only ring that is flat. If I ask you for an angle within an equilateral triangle, you would hopefully tell me it was 60 degrees. So, with cyclopropane, what's the angle between the bonds? Ah, I've caught you out. It's not 60. There's something weird going on here. The angle between the bonds is actually 104 degrees. When I say bonds, I need to be a little more precise. The angle between the orbitals. What's happening? Well, the sigma bond is warped. It's a kind of bent bond because it's under so much strain. For a cyclopropane, most strain is coming from angular strain, and these are called banana bonds for what I hope would be obvious reasons. They make the bond weaker. It's easier to break that bond as a result. What else is happening? Well, let's take a look at cyclopropane. We're going to use our eye and look down this particular carbon-carbon bond and imagine what we see. Let's draw this as a Newman projection. Once we have the Newman projection, it's immediately obvious that we do have the eclipsing interactions. And where there are eclipsing interactions, we know there's going to be torsional strain as well.